And let me introduce the second speaker. This is a talk entitled Low Capacitance High-Speed Phototransistors with a Large Absorption Region. The speakers are from Professor Yablanovich's group, and I'll be introducing Chris Keraly as a speaker.
Okay, well, I can already start by saying that I'm kind of excited to give this talk because yesterday we heard all about the systems guys saying that they don't have enough bandwidth coming to their chip. And so this is potentially a solution for that. And then this morning we heard about the TFET guys saying that they have tremendous problems to achieve their sub-threshold swing. And I think we don't have quite the same amount of problems. So we have a low-hanging fruit, in my opinion. So I'm going to talk about how we can hope to reach the quantum limit for photo detection in optical links. And to put this a little bit in perspective for those who don't know the field at all, at the bottom here, is this the laser? Oh, yeah. So here's a silicon photonics chip where you have the fiber coming in that comes on the silicon die and the laser module that's mounted to this. This is from Luxtera. And so if you zoom in here, you can see the components in here. So you have the electronics, and you have the silicon waveguides on the chip in which the light is routed. And then that light is routed to germanium photodetectors, where you have an even closer zoomed-in iteration of one of these. And so you've got a really integrated system for our transceivers today. And this is what's being commercially, I believe, getting on the market right now for these big data centers. So let's have a little look at the photonic link energy consumption. And this is actually an analysis that was done by our moderator in one of his papers. So you can ask questions about these numbers to him. But basically, we're about, for the total link energy, it was calculated to be about 2.5 picojoules per bit. And I remember listening to a panel a couple of years ago that said, guys, you need to get below a picojoule per bit, or even 1/10 of a picojoule per bit. So obviously, there's a lot of work to be done here. And this was the sensitivity that was assumed was about 12,000 photons per bit at 12.5 gigabits per second. And so if you look at the pie chart of the energy consumption here, well, there's obviously one huge component here, which is the laser. So, quick conclusion, wow, we need to make that laser a lot better. But actually, the laser wall plug efficiencies today are already almost at 10%. And the quantum limit is 20 photons. So if you're at 12,000 and you can go to 20, you have 3 orders of magnitude to gain on the sensitivity so that you could cut your laser power by 3 orders of magnitude versus just struggling to make the laser come to 100% and only cut 1 order of magnitude on the consumption of this. And so to convince you that working on the laser is not good enough, even if you reached 100%, the objective for chip-to-chip optical communications and on-chip optical communications are much more stringent, on the order of femtojoules per bit, or tens of femtojoules per bit. And so we really need to do something on the detector side. So here are a few approaches that are being pursued today. So really nice results from Intel on the 8 avalanche photodetectors, where they use a separate absorption region and multiplication layer so that they can absorb in the germanium and use the silicon to do the multiplication, which is much less noisy. They've reached about 500 photons per bit and impressive gain bandwidths. But if you work, there's excess noise that are involved with APDs. And if you work for Eli, you know that you can only settle for the quantum limit. So any kind of excess noise is completely unacceptable. So other approaches are building phototransistors, which don't have this problem. This is an attempt by A-Star, where they built a vertical illumination phototransistor out of germanium on a silicon substrate. And, but you can see that they only have 1 gigahertz gain bandwidth. And that's kind of a fundamental issue for phototransistors. And I'll get to that in a little bit, because that isn't sufficient. And finally, you have approaches that involve bringing the photodetector as close as possible to the amplifiers and diminish the parasitic capacitances, which is kind of the same idea of using a phototransistor. It's to diminish the parasitic capacitances. And they've had pretty good results at MIT with 1,500 photons per bit at 5 gigabits per second. So what are the requirements for ultra-high sensitivity? Well, if we just look at a very simple circuit model for either a PN photodiode on a normal bipolar transistor or a bipolar phototransistor, those systems are very equivalent. We can get, given some assumptions, of course, to a very simple expression of a minimum number of photons you need to use to communicate a bit of information at a given bit error rate. So 10 to the minus 9 in this case. So this is the only equation I'll bore you with, but I'm going to go really quickly over the terms. 72, that's just a prefactor that includes a bunch of 2 pi's and the signal-to-noise ratio. Naturally, you've got underneath the absorption efficiency of your detector. If you don't absorb all your photons, you're obviously going to need more photons. And finally, under the square root, this is the more electronics part of these devices. You have the transit time of your amplifier. So that would be, in the case of the transistor, your 1 over ft, basically. Or in the case of the bipolar transistor, the transit time through the base collector region. You've got C naught, which are all the static capacitances involved in your detection scheme. So in this case, it would be the PN junction capacitance, the wire capacitance, 200 attofards per micron. That's pretty huge. And the different junction capacitances in the transistor. In the phototransistor, it would be the 2 different junction capacitance, the emitter base and the base collector junction capacitance. Finally, underneath, you have the bit rate, that big T, that's the bit duration. So the faster you try and go, the more photons you need. And finally, 6.4 attofards, which is just V thermal over Q. So that's kind of, you have 2 dimensionless ratios, which is kind of nice right here. And of course, this is a little bit of a simplified approach, but it gives you the right tendencies, the right, yeah. So for bipolar phototransistors, transistor, let's look at this equation a little closer. You want to shrink, you want the minimum number here, so you want to shrink tau, and you want to shrink C naught. All the rest is, it's the systems guy who decided, right? You can't lower your bit rate, they won't be happy. You can't lower your SNR, they won't be happy either. So you can only work on the transit time and the capacitance. So how do you shrink the transit time in a bipolar phototransistor? You got to shrink the base collector junction, because that's where a lot of the capacitance happens. That's where a lot of the transit time happens. Your electrons flow from the emitter to the collector. They've got to go through this area, so you've got to shrink this. To shrink the capacitance, you've got to shrink the area. So basically, you're going to shrink both this dimension and the overall area of your base collector junction. And what's that? That's exactly where you want to absorb your photons. So if you want to to diminish these 2 terms, you're going to have to shrink your phototransistor so much that eventually you just won't be able to absorb any photons in it because it's going to be so small. And then, of course, your ADA isn't very happy. So the conclusion here is that you can't improve the phototransistor performance without drastically affecting the absorption volume, unless you have a trick to decouple the 2. And this is where we present our new phototransistor concept, which decouples the gain and the absorption mechanism. So what we do is we modulate the base collector junction. You have a shorter junction right underneath the emitter where the gain's going to happen, where your electrons are going to transit, where your amplified electrons are going to transit, I should say. And you have a much deeper junction between in the rest of the transistor where there is no emitter, so that here you can absorb photons. And the trick is that your photons need to be, your photo carriers need to be collected, but they don't need to be collected much faster than the bit rate. Your amplified electrons, they need to transit much faster than the bit rate because that's what gives you gain. So basically, you've got 2 separate regions. One with a short depletion region, a small area, so low capacitance and fast transit time, and one with a long depletion region so that you have a large absorption volume, low capacitance per unit area, and basically you get the best of 2 worlds in one device. So if you don't trust my intuition, here's a simulation of such a device, all in germanium. So this is a pretty basic simulation. And you've got this self-aligned collector implant. And by the way, this is something that they've been doing in BiCMOS for a while. And you can see that with it and without it, for an optical pulse, you get a much faster and much higher gain response if you have this self-aligned collector implant. So let's go back really quickly at ultra-high sensitivity and what the requirements are. And so here's a graph where I've kind of plotted this equation out. You have bit rate on the bottom, detector capacitance on the left axis here. And minimum photon per bit is color coded. So obviously, if you want to go faster and if you have a detector that has a huge capacitance, you're going to need a lot of photons per bit. If you accept to go slower, or if you can lower the capacitance of your detector, then you can work at pretty low photon per bit number. So often Eli says that the nano LEDs could go up to 100 gigabits per second. So if you want to be near the quantum limit at 100 gigabits per second, you're going to need a detector capacitance area less than 10 attofarads. So you really need to make a tiny detector. Now, if you make a detector so small, once again, you're going to have trouble absorbing the light. And so by looking at the data rate and the minimum capacitance you want, well, you can determine what kind of cavity you're going to need to put it in, because you're going to need to put it into a cavity in order to enhance the absorption. So here these lines tell you how much of a cavity enhancement you're going to need to your absorption. So if you're going to work at the 100 gigabits per second and with a detector of 10 attofarads so that you can be in this really low photon regime, well, you have to put it into a cavity with a Q of about 10. And it turns out in a silicon photonics platform, that's not so hard. There are solutions to put detectors in cavities. This was a work done from Ryan Going, who worked in Ming Wu's group about a year ago. This was actually previous work, and he demonstrated a cavity, a metal optic cavity with about 50% efficiency, and only 100 attofarads of capacitance for the detector. So those are pretty low numbers, and those could enable you to absorb most of the light and yet keep really low capacitance. You could also do a cavity more inspired by photonic crystals, and in very simple simulations, if you accept that you'll work at 1310 nanometers, which will absorb a lot more of your light, you can reach extremely low capacitance and yet still keep high efficiencies. So the conclusion of my talk really is that there is a pretty good path towards getting close to the quantum limit for photodetection. It's not that that impossible. We don't have to eliminate all the defects out of germanium like the TFET guys have to do to get their technology working. So maybe we'll have an updated number in a later talk about how many photons per bit they're using in Luxtera in their newer systems. But even if you look at silicon germanium bipolar transistors that are available commercially today, if you design it smartly, you could hope to reach, on the order of 500 photons per bit, and that's today. If you look at this, is numbers straight out of the ITRS in about 10 years. We'll be able to make transistors that are small enough, low enough capacitance, and fast enough to get really close to this quantum limit. So it's a pretty positive note, and I think there's a pretty low-hanging fruit right here for us to go after. Thank you.
I think we have time for one or two questions. Yes?
So how far away does the first circuit need to be from your transistor? Meaning where the waveguide is, and have you looked at that?
So, well, depends. Oops. Depends where you want to be here, right? So, if you want to be in this really high efficiency regime, that's about tens of attofarads. A wire is 200 attofarads per micron. About 50 nanometers. So 50 nanometers is okay, right?
No. I mean, just in terms of the confinement of light in the waveguide, how you need to clear some area around the waveguide to get to the circuit, right? Yeah.
So yeah. Well, are you asking like from a manufacturing point of view?
Well, just from the limits, right?
If you really want to get to the limit, you can do this, where you don't need to separate them. They're integrated together, right? You have a phototransistor right there, which will have a large absorption region, low capacitance, and the gain stage integrated right into it. You don't need a wire. So that's if you want to aim for the super low capacitance. If you want to aim for the last photons per bit, you can do that. If you want to go for an intermediate step, you can do something like this. And in this case, the waveguides are 500 nanometers wide, but you could redesign that. You could there's other configurations that you could use and to try and make this link as short as possible. Yeah.
Okay. Thanks.
Any other questions? Well, we'll save them for later then. Thank you very much.
Our next speaker